Okay, just as a side note, well, first of all, this is again using system dynamics, but it's also using some operations research and basically optimization. Integer based optimization. And in fact, just today I got asked if I could present to the Canadian Operational Research Society in September. So I might present this because they wanted to know about system dynamics, but I know that the operations research is really interested in optimization primarily. So maybe this combination of optimization and system dynamics with resilience in mind might be a nice presentation for them in December. So anyways, this is on supply chain disruptions. And it's very simple type of discussion I'm going to have. Let me get into it. It's a short presentation. So I'll have an outline or an introduction, and then I'll talk about the scenario that I'm thinking of. It's an actual company that I'm working with who has this problem, and or well they're not, they don't have the problem, but they would like to prepare if they get a problem like this. And I guess maybe they already had this problem during COVID. I'm not sure. Anyways, but they're interested in helping themselves if this kind of problem occurs again. So the idea is we have a supply chain disruption. In this case, it's only for a few months. It's not like COVID for many months and years. It's just a few months is what I'm simulating in my system dynamics model. And then I talk briefly about some short-term strategies that people can employ to get over this supply chain disruption. However, those short-term strategies are just band-aid fixes, and the long-term strategies is what I'll primarily talk about, which are, I believe, actually solutions to the problem. And one I'm going to talk about is solutions to this disruption through buffer stocks and inventory. And I'll show you how much resilience you can get if there's a disruption, if for various levels of inventory. And so I'll have some key takeaways to finish. So the purpose is to analyze resilience in a system of two small vehicle fleets. And these are small vehicles and small fleets. So it's a double message there. And I want to understand the impact of a supply chain disruption. Basically, we had a vision of the situation of the standard operating procedure of a one-day delivery of spare parts, and then a disruption which led to a 10-day delivery, and how that would impact the availability of the fleet. And then so I'll explore strategies to restore and enhance resilience. So the system involves a sales fleet of 6 vehicles, 3 different types, compact sedan, SUV, and a service fleet of 10 vehicles, 4 vehicle types, van, pickup, heavy truck, and electric vehicle. And the key metrics are availability, which is the percentage of the fleet in operation, and investment in spare parts inventory. So basically, that's a classic operations research problem where you want to maximize availability with a certain budget, or you want to minimize cost with an availability target. So I've been doing that for many years in national defense, and I revisited that work and developed an optimization program for this example. So the normal operations, as I said, the standard operating procedures is one-day delivery of spare parts. And so we have a maintenance request, and if the spare part that we need is not in the inventory, we do a spare parts order, and we get a one-day delivery, and then we replace the part, and the vehicle is back in operation. And so with this scenario, And with what I optimized as the inventory buffer for this kind of a short lead time of 1 day, I estimated that we could get minimal downtime, that is a 98% availability, with a small inventory of parts for both fleets combined, for about $15,000. These are modest parts, but anyways, so this is like the situation, the sort of the best case scenario. And this is the optimization. So you see, it's a classic diminishing returns, and you can see why I picked $15,000, because with no inventory, you're only getting a little over 50% availability, and as you increase the inventory, you get steady gains at a diminishing rate. And then after about $15,000, you're not making hardly any improvement at all. So if you're looking for the best bang for the buck, you might choose $15,000 if you were confident in the 1 day delivery. So now we have a disruption, which causes the delivery delay to be 10 days. And I assume the disruption starts at month 1 and lasts for 3 months. So it's a very short disruption, but it does create problems with the availability of the fleet. So we have causes, obviously, could be shipping delays or raw material shortages, and the impact is that when we look at the steady state, with the optimized inventory buffer of only $15,000, then the availability drops in the steady state from 98% to 48%, which is quite a significant drop. And if we look at the new optimization, this is the disruption. So here's the system dynamics aspect of it, and you can see the disruption occurring in month 1, and because of failures in parts, the availability starts to drop, and by month 4, it's still declining when the disruption stops or changes, and then we get back to the original state after about 8 months. So this is, I think this is a very classic look at how resilience can be modeled with this kind of scenario. And if we look at the optimization, again, now with the 10-day delivery delay, then we see that, as I said, with $15,000 in the inventory, we're up around 50%. And then, so we might want to increase it to $20,000 to get more buffer. $25,000 will give you 80%. But you notice that the diminishing returns is really slowing down after about $25,000. So I'll look at those scenarios. So here's some short-term strategies. So now that, as I said, those were the inventory buffers is more of a long-term strategy, but the short-term strategies are to redistribute fleet resources and prioritize vehicles based on demand and availability. So basically, you may cut back on operations and just do the high demand or high priority operations, and only use vehicles that are available, obviously, so that you get the priority jobs done. The other thing that often happens in real life is cannibalization. It's not an optimal strategy. It's basically a band-aid solution. But basically, what happens in cannibalization is that say a vehicle goes down, it has a part that fails and can't be replaced. So now that vehicle becomes a stock of parts, and the vehicle is then left down for the period and robbed of parts to supply parts to other vehicles as needed. So Cannibalization is quite common in real life, but it's not. It's definitely not a solution. It's just a band-aid. And then long-term strategies is the best strategy I can come up with for this kind of scenario is use of inventory buffers and identify high priority parts and increase the local stock. And again, I optimize this. I try to get the best mix of parts to get the best availability at minimal cost increases. And then diversification of suppliers, definitely, having multiple suppliers can avoid disruptions from a single source, but in my model, I was sort of looking at the fact that maybe all the suppliers were having the same problem, and so this wouldn't really help if the whole industry was suffering from a lack of raw materials, for example. So I'll just get into the inventory buffers. So here's some examples of different delay lengths for the $15,000 inventory. So you can see that the 10-day delay is shown in orange. 15 day delay is even worse, and a 5-day delay is relatively much better. The resilience is much better. And then if you look at a $20,000 inventory, you see that the results are significantly better. So if you go back, you see the results of a 5-day delay, a 10-day delay, and a 15-day delay. And then if you get to $25,000, and an optimized inventory, you can get very good results. So you can see how much improvement you can get in the resilience of the fleet with this extra inventory buffer.
Can I raise a question?
Sure.
Yeah, go back to the curves, either one. I'm a little surprised that the recovery isn't linear. Why is it showing an exponential recovery rather than a linear recovery?
It's primarily based on the way the delays and system dynamics work.
Yeah.
They're not linear. Generally, system dynamics shies away from linear viewpoints and has a nonlinear perspective on things. So
But
so
if
it's
I had
primarily an issue with the system dynamics model.
but if I had 10 trucks down and I need one part to get each one of them back online, and I get a delivery of one part per day, the recovery is going to be linear.
True, but we don't have we have more than one fleet. We have a fleet. We have two fleets, and those fleets are made up of multiple vehicles. So when you combine all the fleets together in one giant availability measure, you'll get this sort of randomness in the recovery. So one vehicle, you might get the part for that vehicle, but another vehicle you may not get the part at the same time. I don't know if that helps at all.
Okay, well, thank you.
Okay, that's it. My key takeaways are that resilience is critical in managing disruptions effectively, as we all know, and that short-term measures can stabilize operations, but long-term strategies can ensure future disruptions have minimal impacts. And so that's my presentation.
Yeah, Ivan, a brief comment regarding if I can use the curse word just-in-time inventory control.
Right.
We've talked about this offline, and that is JIT has been all the rage in industry for some time, because if you have good control of your supply chain, then you can, shall we say, optimize your overhead and the like to do things in such a way as to maximize your profits or minimize costs. But all it takes is one little disruption and kablooey, you're in trouble. You fall off the cliff.
Yeah, like I said, the way I was thinking of modeling it was with less than a day of delay. So
Right.
you might have, say, an hour delay or a 2 hour delay to get a part delivered to, from a close by supplier. There's no reason why I couldn't model a 2 hour or 1 hour delay. And then I would obviously get a much better availability with, for example, zero inventory.